Okay. So last meeting we had, we talked about the flash calculation, the so-called Ratchford Rice algorithm, and today we're going to do an exercise with that calculation. And in addition, we kind of rushed through the equations for doing a saturation pressure calculation as well, bubble point pressure and dew point pressure. So we'll also do something on that. Are there any questions before we get started? What we're talking about is having a given composition expressed as a molar composition Zi, and in the flash calculation we want to specify a pressure and a temperature, and we want to calculate the amount of moles of each phase, if it's one or two phase, number of phases, 1 or 2, and the amount of each phase, and the phase compositions. Yi and Xi. And the amount of each phase, we can express it as moles, but we introduce this vapor fraction, gas phase fraction, the total moles of the gas phase or the vapor phase divided by the total moles of Zi. So that was just defined as total moles of the vapor phase over the total moles of the system. That was the flash calculation, and if we plot pressure versus temperature, we've got a phase diagram for a mixture. I wanted to do this in color. We've got maybe along here we've got bubble points. That means that this composition, Zi, at these temperatures here, below this particular temperature here, form a liquid with a bubble of gas at these different pressures. And then at higher temperatures, we get dew points Again, this is the same composition, but we're changing temperature. And we're getting dew points here out to this point here, somewhere around here, for example. And then we have another dew point that it starts finding. It's called the lower dew point. And that curve will look something like this. And it'll hug very, very low pressures here. Finally start increasing there. So these are the lower dew points, and these are the upper dew points, where you have that composition being a gas phase with a small drop of liquid. Yeah.
There are some points that we cannot tell that at that point we have steam, in liquid or gas.
Yeah, the point where you don't know if you have liquid or gas would be, okay, so inside here, we have two phases, a gas plus oil, or vapor plus liquid, as you like. And along the lines, the green line, we've got this mixture containing, basically, it's full of what we would think is oil. But then there's some little gas bubble there. You probably can't see it on the picture, but there's a little gas bubble. And if we took that same mixture over to a higher temperature, maybe to this temperature here, the volume of the container might be a little bit different, but we would actually see a gas phase, and we would know a gas phase because there would be a little drop of liquid there. So you can actually see two phases. Well, see. It depends how small the bubble or the drop is. Okay, but if you move just slightly on the inside of that line, then you'll see enough to identify it as being two-phase. Okay? And then the question was where you don't know that it's gas or liquid, but that it's just single phase. And that's everywhere outside that diagram. Everywhere. We don't really know if it's a liquid or a vapor. So outside here, we have a single phase. And we can say that it behaves like a liquid. It's got a viscosity greater than 0.1 centipoise. If we want to call that our religious definition of a liquid, if it's less than 0.1 centipoise, we'll call it a gas. But you might pick 0.2 centipoise, or you might be a difficult child and say, I choose 600 centipoise. Okay, anything less than 600 is a gas, and you would have the right to do that because it's an arbitrary definition. It's single phase. But you can say it's gas-like or liquid-like, and you typically key that off of density or viscosity. Okay? Now, in the industry, we do generally say that any system that is below this special temperature here, connecting the bubble point and the dew point, which we call the critical temperature, we formally, politically, governmentally usually define that if this composition Zi is at some reservoir temperature less than critical temperature, then we call it an oil. Okay? Even if the pressure is way up here. We call it an oil. That's what we do. And if the temperature in the reservoir is greater than Tc, then, say the pressure's over here, then it's called a gas reservoir. Okay. But that's kind of our arbitrary definition. We do that so that we can say what we have. Okay? But it's arbitrary. Because as soon as you say, oh, that's a good definition, then what we're going to do is that I'm going to say, okay, let's take this composition and let's put it in a reservoir. Get this thing to draw. And this is a geologic zone. And everybody's had geology, right? And you know there's something called a big fault. Okay? So we're gonna say that there's a big fault, and then this same reservoir, maybe another fault here. Okay? And let's say that we've got a water contact. So we got water down here. We've got our Zi here. That's what's in there. And then down here we've got no water, but we've got the same Zi. Because originally those two were smacked up against each other and contained the same fluid. And then somebody, God or whoever you believe in, decided to break this piece of rock into two and slide the one down and bring it to higher temperatures. And down here it's 120 degrees C, and up here it's 100 degrees C. And you see my critical temperature of this is 110 degrees C. Okay? And in theory, the pressure could be, like I said, here and here, way up there. And according to this industry definition, I would call this a gas, right? Because its temperature was greater than 110, and I would call this an oil. But you drill into it, a well here and a well there, and you start producing, and you get exactly the same stuff out. ZI. Exactly the same stuff. Of course, you know, the ones who own the left field, they can beat themselves on the chest and say, I've got an oil reservoir. The ones on the right field can frown and shed some tears and say, oh, I've got a gas reservoir, because people generally think you make more money from oil reservoirs than gas reservoirs. But you got the same stuff. So it's a bit arbitrary. But that's what we do. Any questions about this? But even make it more fun, give you a case where we've got just one reservoir, same composition everywhere, but the temperature variation goes like this. And there's my 110 degrees C. Okay? Composition is the same everywhere, ZI. And now all of a sudden we're saying that we've got oil up here on top of gas. Right? Which is starting to not make sense. Intuitively, gas is lighter than oil and it should sink, and you get, you know, so who knows. But so this is why it's an arbitrary definition. It's something we use, but it's not always easy and unambiguous to use. Okay, now what we're going to do today is that we're going to do calculations inside and along the phase envelope. Okay? Inside and along the phase envelope. We're going to do phase equilibrium calculations. That means that we got two phases. And we're going to look for the amounts and the compositions. Okay? So that's the game plan. And I'm going to go to chapter 6, which you'll be reading soon. Next week we'll get started on, next week or the week following. I'm not sure. Probably next week on chapter 6. We have chapter 6 and chapter 7 left to do on PVT when we finish today. And I'm not sure which we're going to do first yet. But chapter 6 talks about laboratory PVT tests. And in there's an oil example, which is what we're going to use, and there's a gas condensate example, which we're not going to use. Okay, and we're going to take this one. And the reason I want to take that one, I'll show you here. Chapter 6, I'm going to copy this table 6.4, which has the ZI, the molar composition, and the reason I decided to use that is because we've talked a little bit about the Troll field, which is Norway's largest gas reservoir, and it's the third largest oil reservoir in Norway. It's got about 4 billion barrels, 5 maybe. And this book here, they used to give it away free to the students. I don't think they do anymore. Anybody seen this before? It's called the SPE Monograph. Anyway, it doesn't really matter. But in the appendix, it has, as of the date of the book being written, which is back in the 1992, it has properties of most of the petroleum reservoirs. Permeability, porosity, what kind of rock it is, and what's inside the rock, approximately. And it says here for troll oil, it's got 36% molar percent, so troll oil. It's got C1ZI 36, this is approximately, molar percent. And then, because it's a book and they're C2 to C4, it's got 7 mole percent. I think it's missing some things. And then it says it's got 40 C5 and heavier. Does that add up to 100? 3, no, not hardly. So it's missing some stuff. I don't know. Well, anyway, let's just assume that the 36 and the 40 are right. And we'll throw together in the C2, C4. We've got some non-hydrocarbons, a couple of percent. So I'm going to change I'm going to change this one a little bit to make it add up closer to 100%. We need 14 here, 15, 24. How much do we need here? Yeah, about 20. And then we got some non-hydrocarbons for something like that. Well, what you see is that in this table 6.4, you've got methane in about 36%. And if you take the C5, which is this stuff here, that's pretty close to 40%. So I thought, what the hell? We'll use this as a surrogate, as an approximation for our troll oil. At least when we calculate on it, you can feel like you're doing calculations on something similar to Norway's third largest oil field. So we'll use this composition for our calculations. So this is going to be our Z reservoir I. Okay. Then we need some K values. As you remember from the last lecture, we need K value estimation. And we're going to use this so-called modified Wilson equation. Which is in chapter 3. And there we are. I'm going to snatch this one. Put it over here. And what you see is that it's got, for each component I, we need to have PCI, and the reduced temperature, TRI, is just the absolute temperature of whatever we want to calculate at, divided by TC of I. So we need the TC. And then it's got this acentric factor we've talked about before. So we need for every component in our system those three numbers. This PRI is raised in hell, they call it back home. All right. So we got the reduced pressure, so we need the PCI twice. And then we've got this thing that we don't really know what it is, the convergence pressure. And then we've got what's called A1. And it says that A1 is a function of pressure. going from A1 equal to 1 at close to, atmospheric pressure, and A1 going to 0 at the convergence pressure. So it's going to look like this. Pressure, PK, P standard conditions goes from 1 to 0. So it's, there and there. Now it could be a straight line, but it actually, if you go further into the text, it gives us actually an equation that we can use approximately, which is 1 minus P over PK to the power of A2, but A2 is somewhere between 0.5 and 0.8, and we're going to take a vote. We'll use 0.7. Is that okay? Yeah. Okay, so we can say that our A1, and that'll look something like this. It'll have this kind of shape. Okay, so that A1 approximately equal to 1 minus pressure divided by convergence pressure, and that ratio to the power 0.53. You don't care. Okay, we'll use 75, just because we got some resistance out there. I don't want to be like Mitt Romney and just tell you what you want to hear. Give you a little resistance. 0.75. Okay? So, we got a little bit of work to find our K values, but once we get these properties we'll get from Appendix A, maybe Chapter 5 we'll get for the C7 plus. And we'll do some kind of guess to begin with of the convergence pressure. I told you it should be at least higher than the saturation pressure. I think I told you. And in Chapter 6, the bubble point of this system, this is measured, is around 20. I think it's around 2,800 psi. I think we could look for that. Chapter 6, somewhere. It's 2620. You don't need to worry about that. It's here. So it's about 20. It should be 2600. In fact, I'll just write it equal to 2620. And you have to be careful because laboratories usually report not in PSI-A, but in PSI-G. Let's just check that. PSI-G. So we'll write PSI-G here. So that's 2635 PSI-A. Okay. So the convergence pressure needs to be bigger than that. Okay? And shoot. I'll just give you a number so we'll guess something, maybe 5,000 psi to start with, to do our first calculation. And then I'll show you a better way to figure out, instead of guessing, how to come up with a better number. We'll just start with a guess. Okay? So we've got an equation for K of I. We've got a composition down here, Z of I, and just call it Z of I, in the reservoir. What else do we need? We need to get some of those component properties. And the component properties we can pick up from Appendix A, Table 1. Table 1A is in my units, and Table 1B is in most of your units. But what we see is that we've got critical pressure, critical temperature, acentric factor, and so forth. So we got the things we need. And then we need to remember the equation that we're going to solve. That may be harder. Ratchford-Rice equation. And that was to solve h, a function h, as a function of vapor fraction. And that was equal to the summation of I think I'm just going from memory. I don't really remember this. One plus f. Is this right? Or not? Does anybody have that written in your notes? Is that okay? And we want that to equal 0. Or we can solve the Muscat-McDowell equation, which was Zi over Ci plus f of v, where Ci is equal to 1 over Ki minus 1, but Ci is equal to 0 if Ki is equal to 1. Okay? And we also want that to be 0. That would be just a different form of the same equation. This is the Muscat-McDowell equation. 1949. 1950 something. 4 or something. Okay? And we have to remember that the f of v that we want is going to lie between f of v max, which was 1 over 1 minus k minimum, and it should be greater than f v min, which was equal to 1 over 1 minus k max. You think I'm smart and remember all these equations and stuff. It's not really true. My boy, who's not here with us today because he had better things to do, he gave me a math problem. He had a math test today, and he gave me a math problem yesterday. I had no chance to solve it. I mean, I tried and I racked my brain, and you guys probably all will solve it right away. This is being recorded, so all the professors in the world who will, listen to this lecture, which will be equal to 0, could laugh at me. But the problem was this: x minus 1 times x plus 1, where x is supposed to be a whole number, or not a whole number, an integer. I guess a positive integer. X is an integer. I guess I think it's got to be greater than 1. Something like that. Anyway. And you're supposed to prove that that thing, for any value of x, could be divided by 6 with what do you call it? Kind of modulus 6 or something. That you can divide by 6. Okay? And it still ends up being an integer. Now, whoever figures that out and comes during the break and tells me, I'm not going to kiss you and I'll shake your hand, but I couldn't do this. So the fact that I remember these other equations is simply because, I don't know, I don't have a life and they just kind of come back sometimes. So we got to solve these equations. I'll just kind of do this so we don't think it's part of the material. give it to you a little bit darker just in case you're really interested. Okay. Okay. Now we have to figure out how to solve this. So we're going to use Excel, and I'm just going to go through the steps of all the boring steps of doing this, and then eventually you're going to have to do this yourself because the next exercise will be doing this. Okay? So go up to Excel. And by the way, problem 1, most of you did not turn in an Excel file, which actually was required. Well, required. I didn't state it explicitly in the problem 1, I don't think. A lot of you gave a PDF file of something. I didn't see the exercises, but my student assistants told me. And that was not good, because I thought I had in the problem, I usually write it, but I didn't. And in the data information thing, I thought I'd said that you're supposed to turn in all your problems in Excel. These should be solved by programming and or using a spreadsheet program such as Excel. That's kind of, okay. Most problems will be partially solved in class, like today. And then I said, turn in problem solutions electronically through its learning, The point was, I was trying to say, what I should have said is that turn in your solution in Excel. And if you want to add a PDF file with notes or something, great. Turn in 2 files. But the reason I wanted you to turn in an Excel file is because I want to fail your butt if you don't make good Excel files. Okay, I want to force you to learn to do good Excel engineering. We've already had lectures about this. And if you don't turn in your Excel file, you're kind of hiding from me. You're hiding from the whip I want to use to teach you to learn how to do Excel, to use Excel as a good engineer. So, but it's a little bit late to have everybody turn in problem 1 again. So, originally I thought, well, I'll just make you all do it again. But I'm not going to do that. But that means that the second problem you're going to have, which is going to be something like we're doing now, is going to be in Excel, and they're going to be even stricter. Okay? So the best way to cruise through this thing is to just follow how Curtis does it. And you don't have to make it fancier, but if you make it sloppier, whip may come out. Okay? So I'm kind of like, I do minimum of what I accept myself. So that's good. So we're gonna go in and do this. So okay. So this first one's just going to be flash calculation. And I'm going to write isothermal flash calculation using Ratchford Price Ascot. Okay. And it's September still, 25th, 2012. Okay. Now, I've got to input some numbers. And certainly I have to input the pressure and temperature, right? So, and I'm going to give myself a little bit of, I'll give it in PSI. What units do we want to use? How many want to use PSI units? Not too many. How many want to use bar? All right, there you guys win. Bar, absolute, and degree C. Okay. We'll do a simple flash at standard conditions. Conditions here in the room. 56. That's not too far from that. It's a little more, I don't know, how does it feel? Yeah, we'll just say that. And these two numbers, because I input them, are going to be in red. And in your Excel sheet, well, you don't have to use red. You can try using blue. Okay. It's terrible. You know, even my kids don't listen to me. My wife certainly doesn't listen to me. And I've got a little bit of the fear of God in you guys. So I'm hoping you do it in red. But, you know, you can do it in pink, or just make sure it is clear. But if you don't do it in red, you have to at least put up here that input numbers in, yeah, right? Red. All right. And I'll even make it just to kind of like point out. Okay, or you can use pink or purple, whatever you want. Don't use gray or something that's so close to black that you're just being ornery. Okay? So we got the pressure and temperature. Now we're also going to need the temperature in absolute. We already know that, right? So I'm going to go ahead and stick that here below. You don't have to do it this way, but and we'll say equal to the degree C plus our 273.15. Okay. And then we've got our components, right? Nitrogen, CO2, methane, ethane, butane, propane, isobutane, normal butane, isopentane, normal pentane. These are the components that you'll for sure always see. And then C7 plus. Okay, we got the components. And then I'm going to put the component properties and well, first we have to put the amount, the mole fraction. Okay, so Zi. I like to put the unit below it. In this case, it's going to be mole percent. I like to have all these headers and their units centered. Okay. Okay, so then I got to punch in these numbers. And if I'm lucky, should only be so lucky. Now, why didn't it? Let's see. There we go. Copy. Paste. And of course, it's not right. They have to make sure. And by the way, this is an important part of being an engineer, is that you have to assume that when you did this copy and paste that you did it wrong. And what could you have done wrong? Well, the component order could be different. So nitrogen, the CO2 is first and then nitrogen, so it's switched around. Okay, so I need that 0.3 up there and the 1.62 below. Okay, that was my first mistake. And the other thing is that this is the first stage separator gas. Damn, that's the wrong table. It should have been 6.4. You guys are supposed to pick up on this. Okay, this is not my responsibility. It's your. Okay, so we'll pull that in instead. Hold the whole. Everything was wrong. Okay, and now we got these are reversed, so I got to go 0.91 and 0.16. And then if we just kind of grab onto them, you can see down at the lower right it's 100. But I want to actually put a sum down here just to keep things honest like that. Okay? Now these numbers were hand entered, right? More or less. Red. And at this point, you think I need to say, because it's Microsoft Windows we're using, so we need to class problems. Just put it over there, and this is going to be Flash PSAT. Just okay. So we got the file there. So then we need TCI in Kelvin, PCI, bar, absolute, and the eccentric factor. And there's no unit on that. I don't have the omega. Okay. I think you can do it. I generally would never waste my time doing this, but you can do this if you go to symbols. I think do this just for your sake. Okay, but you know that's not required. Okay, you can still pass without that. Okay, so now I got to go in to the Appendix A and pick those numbers up. And those were, in fact, it's got H2S hidden in there, but that's all right. So that third one is 0.1 is H2S. We don't need that. So what we'll do is that we'll just drag these up here. Okay. Make them look kind of nice. Same number of digits. And then pick up the PC. Uh-oh, it's kilopascal. They're down to C6. Now, I don't know, is this a number or is it just showing as with a space in there? Are they the wrong order? I messed up. Okay, should have done this. Thanks. Okay, but what I don't know is that these don't look like numbers. Man. At this point, you're starting to wonder why you became an engineer. I can only say that when I was your age, I was doing this with a calculator, each number punching in. Okay, so we got, and this is not bar, but in kilopascal. And then the TCs. And then we want to get rid of this one, H2S. H2S is kills. It's like drugs and driving too fast. And and it doesn't take very much H2S to kill. So we're getting rid of it. In Norway, we're lucky. We don't have much. We don't have enough to really kill with. So there's TCs. Then we're going to have to come up with something for the C7 plus. And to do that, we're going to go to chapter 5. And to do that, we're going to see that the molecular weight of the C7 plus is 218. So I'm going to go look for any old thing in the book that has a molecular weight about 218. It needs to be a hydrocarbon. And just look for its critical properties. And in chapter 5, table 5.2, there's these yahoos, cats and fears of body. Remember I told you about them? Yeah. They gave the table. And we'll go into that table now, chapter 5. Table. There it is right there. And do we have it in Kelvin and stuff? Nope, unfortunately not. So we got to be careful. So a molecular weight. These are hydrocarbon fractions, like, if you got a C6 or a C7, or in this case, we're going to kind of assume it's like some kind of average. So it's 200 and what? 12? 218. So that's close to 222, right? I mean, for the kind of thing we're doing, it's close enough. So we're going to pick up the critical pressure, temperature, and eccentric factor there. Those are in the wrong units, but we'll just bring them over. Okay, so, and that's TC is the first one. So 1321, and to convert to Kelvin is divide by 1.8. Okay, a little too few digits. And then next one is 253 psi. And now it's 0.1450377. Why? I don't know. You divide by that to get kilopascals. So 0.1450377. And that should be there. And the eccentric factor should be okay, 0.684. And then this is a text. I'll just delete that. So now we've got our critical properties. Anybody say anything done wrong? Of course, that error would have stayed on. Okay. So it's time for a break. And I'll just pause this.